the North America, okay? Tonight we are going to have a very interesting presentation. Actually, we do have two presentations. One of them will be made by the Professor Saifur Rahman, and then the second presentation will be made by two persons, Dr. Farid Khatari and Shadi. It's difficult to pronounce second name, Shadi, and Kwan Fishes, I think I'm sure that, yes. And then, so after this, during the speakers, if you like, you can send the question directly to me, to any one of the speaker, or to three of the speakers, okay, if you like. And then at the end, I will ask the question. I will forward the question to the speakers. So, and firstly, I would like to introduce the Professor Saifur Rahman. But before this, Professor Saifur Rahman is a candidate for the position of 2021 IEEE President-elect. And along with the Professor Ray Luye from the University of Maryland and Professor Ramesh from California University. So, Professor, if you come to a short bio for Professor Dr. Saifur Rahman, is the founding director of the Advanced Research Institute at Virginia Tech University, US, where he is the Joseph Loring Professor of Electrical and Computer Engineering. He also directs the Center for Energy and the Global Environment. He is a life fellow member of IEEE and IEEE Millennium Medal winner. He was the president of the IEEE Power and Energy Society for 2018 and 2019. He was the founding editor-in-chief of the IEEE Electrification magazine and the IEEE Transaction on Sustainable Energy. He is a distinguished lecturer for the IEEE Power and Energy Society and has lectured renewable energy efficiency, smart grid engineering, internet, blockchain, Internet of Things, sensor integration, etc. in over 30 countries. Now, he is a professor at Virginia Tech University. The second speaker will be the Farid Khatari from the Kanda Technology. Farid is Vice President of Advanced Technology Integration for Quanta Technology. He has more than 15 years of professional experience in the area of distinguished and renewable energy sources, microgrid, and application of power electronics in power system for non-wires alternative. He is a senior member of IEEE, and he represents the representative of the IEEE Standard Committee in IEEE Transport, Electrification, Transportation, and Electrification. And then Shadi is a principal engineer and grid business and product lead with the Advanced Technology Integration Group at Quanta Technology. She has over 5 years of industrial experience in the area of distributed energy sources integration, terms, microgrid, and battery energy storage solution. Shadi has been a part of IEEE organization since 2009 as a member of IEEE and IEEE Women in Engineering. Now I'm going to give the floor to Professor Rahman and then to start his speech. And the subject is engaging with the global environmental issues through the engineering solution. Rahman, Professor Rahman, the floor is yours.
Thank you, Professor Omer Usta. I appreciate your kind introduction and welcome everybody from Turkey and everywhere else. I will give this presentation in the context of the panel, which is titled Engaging with Global Environmental Issues Through Engineering Solutions. My focus is, this is the next line on my screen, I'm focusing on the global electric power sector and how we, the power sector people, are engaging with the issues of environment And I'll lay out the big picture of the issues and challenges of the environment. And I hope my two colleagues, Farid and Shadi, will go into the more in-depth. So as engineers, we have a complete picture going forward. So with that, let me move on then. This slide you see in front of you, if you focus to the left-hand side of the screen, this shows where are the electricity sources located, and not physical type of sources. Coal is produced in 2017. Coal was responsible for 38.3% of the global electricity production, 36%. Second was natural gas, 22.9. Third was hydro, 16.3. Nuclear, 10.2. Wind is other small, fine. The issue I'm trying to bring to your attention, oil you see here, 3.3%. That means we use oil, mainly diesel and some low sulfur fuel, very small amounts globally, very small amounts. On the right-hand side, the screen shows who are the largest electricity consuming countries in the world. China, number one, by far the largest, about 5.7 trillion watt hours. Then we have US, under 4,000. Then India, Japan, Russia, and so on and so forth. These are the players, top 10 countries globally. Now, let's look at the next relationship. Very interesting. As you know, coal is a significant CO2 emitter, and coal is also a big contributor to the production of electricity globally, 38%. The good thing is, as you see in this picture in front of you, the new coal-fired plants are decreasing very fast. If I look at the left-hand side of the screen, up to 2018, China was using about 2 billion tons a year of coal. Next is India. Remaining is Asia Pacific, which is Indonesia, Malaysia, and Australia, and the rest. And rest of the world under 1 billion tons of oil equivalent coal. That's 18. If you look on the right-hand side of the screen, this shows the future, meaning number of coal-fired generation plant receiving funding, financial investment. 2010, the investment was for 100 gigawatt, or it means 1,000 megawatt plants, 100 of them, right? That's 100 gigawatt. That number slowly decreased. Last 3-4 years, it is decreasing very fast. That means in 2018, the funding was approved only for 22 gigawatt as opposed to 100 gigawatt in 2010. Coal is dropping, which is fine. Now, let's different picture now. This shows on the left-hand side, top 20 countries that emitted the most carbon dioxide in 2016. That number is changed some, but not a whole lot. China was like 9 billion tons of CO2. China 9 billion, US almost 5, India 2.0, Russia number 4, 1.4 billion, Japan 1 billion, and so on. Top 20 countries. In this table, Saudi Arabia was number 10 in terms of total CO2 emission country-wise. If you focus on the right-hand side of the screen now, you'll see which countries are producing the highest amount of CO2 overall. China number 1, we get that. US number 2, India EU and India are close, and then other countries, Turkey only 1%, for example. Turkey has a lot of hydro and so on. So this is the thing. So now keep that in mind, left-hand side, total per country. If I show this to Chinese friends, they say, well, we're a big country, got 1.3 billion people, so don't count the whole thing, count the per person what the number is. India says the same thing. If I go to per person, next page, you'll see China is number 12. India, number 20. Saudi Arabia, number 1. How did Saudi become number 1 from number 10? Here, they were number 10. Here, they're number 1. What happened? Saudi Arabia has much fewer people than China, India, of course. And Saudi Arabia is a big oil producer. When you produce oil, you drill and you use energy to produce oil. And you transport that oil from place one to another place. All those activities require fuel. That's why CO2 level goes up for them on a per capita basis. Now, Australia was nowhere in the previous chart. Now they're number 2, US number 3, Canada, pretty clean because they have tar shale in the western part of the country. They are number 4. So this is the thing. This is a debate globally. How do you count? Count for the whole country as one number, or you count per capita? That debate will go on for a long time to come. India here, number 20. It was number 3 before. Good. Now, this is a different picture. It shows CO2 emissions from fossil fuel combustion. That includes transportation, cement making, and all that, all put together. So China number 1, we expect that. US number 2, EU number 3, India number 4, overall, including transportation. Good. Now, this is interesting topic. We are slowly, globally moving away from coal. China, as you have seen already, is the biggest coal consumer in the world, but things are changing. In 2001, China produced 73.4% of electricity from thermal, mainly coal, some oil and gas, 73%. 25.5% came from hydro, solar, wind, 2001. 2016, that number has grown from 25 to 33.8, and thermal went down. 2018, 37%. 2030 target is 52%, or more than half of Chinese electricity will come from renewables, 2030, 10 years from now. And thermal will be 42%, remaining 6% from nuclear, the Chinese numbers. This is something to watch. As a result, we'll see reduction in CO2 from Chinese power plants. Now, this is very interesting. What is the source of CO2? We talk about power sector, which is fine. So if I go back 10 years from now, or 20 years from now, 2000, electric power plants produce 33%, like steel mill 20%, and residential commercial use 12%. That's 2020 years ago. If I look at numbers today, electric power plants more like 26%, down from 33. Transportation, more like 40%, up from 33. The point is, in the power sector, even if we reduce the use of fossil fuel, for global warming, it's not power sector. Whatever we produce, total count is the big number. So unless we have some more activities to reduce fuel, petroleum consumption in the power industry, in the transportation industry, will not solve the problem. Fine. Now, other question comes up. We all know CO2 is a global warming gas. There are other global warming gases as well. Methane, nitrous oxide, hydrofluorocarbons, perfluorocarbons, and SF6. We are power engineers, many of us. We know we use SF6 for compact power substations and switchgear. We go to a substation which is exposed to the outside. To avoid sparking, you spread them out. If you do a substation indoor or underground, you don't have that much space. Use SF6 to protect against sparking. That's the use for, in our industry, SF6. Now, if you look at the bottom of my screen, it shows emissions of CO2 over time. 1997, it was 30 billion tons of CO2. 2018, it went up to 41 billion tons. Big increase in 18 and 20 years, let's say. Now, let's see, this is a big issue now. We say CO2 is big, which is, we understand, methane is 28 times more potent than carbon dioxide. That means the amount of global warming that can be attributed to methane, CO2 is much, much less per unit basis. But we produce much more CO2 today than methane, by far the most. Nitrous oxide 265 times more potent than CO2. Hydrofluorocarbons, 138 times. Perfluorocarbons, 6,630 times. Big thing is SF6, 23,500 times than carbon dioxide. That means the global warming effect of 1 ton of SF6 equal to 23,500 tons of carbon dioxide. Big difference. That means we have to be careful as the SF6 usage grows globally. Now let's compare the electricity from different fuels, gas, oil, and coal. This is very typical today. If I look at the second row going across from left to right, gas-based electricity, for each kilowatt hour of electricity production, we produce 2.3 grams of NOx, nitrogen oxide, and 0.004 grams of sulfur dioxide, and 490 grams of CO2, about half a kilogram for gas. Oil, the NOx is about the same, 2.02. Sulfur dioxide is
Is Professor Rahman Karov?
I'm not hearing from him. I think it's a general problem then, if you're not also hearing. Yes, he did. And we will try to figure it out and fix it.
Am I back now? I lost the line.
Oh, yes,
Am
you're
I
back, Professor.
Okay, thank you, thank you. So I have to share the screen again. Hold on. I'm sharing now. Can you see the screen now?
Right.
Shimai?
We can see the screen.
Good. So let me move on then. So this is the issue. I don't know if you saw this one before. CO2 is one in reference point, methane 28 times more potent than CO2. Going all the way down, SF6, sulfur hexafluoride is 23,005 times more, 500 times more dangerous. Now, if we keep going this way, we see the three major fossil fuel sources for electricity are shown here: gas, oil, and coal. And we are looking at, for each kWh of electricity, how many grams of this gases you produce. For NOx, you produce 2.3 grams from gas. For gas, you produce 0.004 grams of sulfur dioxide, almost none. CO2, about half a kilogram. Oil is 2.025 and all that. Big thing is coal. For each kilowatt hour of coal-based electricity, we produce 3.5 grams of NOx, 9 grams of sulfur SO2, and 1,090 grams of CO2. Sulfur is not a global warming gas, but it's an acid rain gas. That's why coal is not liked in many places. Today's coal plants all are using scrubbers, meaning as the SO2 goes up, it scrubs it, so SO2 doesn't get released to the atmosphere. Good. So how you solve this problem? Well, obviously, use less electricity, you would be producing less CO2 and less NOx and so on, no problem. Or we can make our power plants more efficient. If you compare a coal-fired power plant today with a combined cycle gas plant, combined cycle is more than 60% efficient, coal is about 42%, the best ones to this, 50% more efficient. That's a possibility, use less fuel. Or number 3 option, produce more electricity from renewables and nuclear. We'll look at all these options. We should at least. Now, then the question is, fine, you talk about renewables, how much do they cost? I'm showing you cost for 7 different types of renewable fuel, biomass, geothermal, and so on. Biomass average is low, about 6 cents US per kilowatt hour, but varies a lot because biomass can be in a forest, in an agricultural field. Many things produce biomass in different countries. The price range is so diverse. Geothermal about 6.5, 7 cents. Hydropower is the cheapest here, about below 5 cents a kilowatt hour. Solar about 6.5. Concentrated solar CSP about 17 cents. Offshore wind about 13, twice as much as onshore. Like here, onshore about 6.5. These are numbers for pricing. Look at this picture, more recent data. Energy costs $1 per megawatt hour. 2009 till 2019, 10 years. Solar was $350 per megawatt, I mean 35 cents per kilowatt hour. It has come down to under 5 cents today. Wind is same thing, under close to 5 cents or just below 5 cents. Coal has remained at about 10 cents a kilowatt hour, global average number. This is fine. Now, let's see what is the bottom line. We have looked at the problems, talk about the solution options. Well, what can we do? If you produce electricity more and more from fossil, non-fossil fuel and nuclear, one solution. However, if we in the power sector keep it down and the transportation sector doesn't do much, then it doesn't help globally. Then you say, well, bring more electric vehicles. We can. The issue is, where's the power coming from to run an electric car? If coming from coal units, it's not as useful as coming from, let's say, wind or hydro or solar. So that's the bottom line in my judgment. Other thing is, my message to engineers, life is changing. I'm showing 3 different things here that is not very well understood always. On the upper left-hand side, I show a boat with a solar panel on the rooftop. That boat is a library in the river in Bangladesh. That boat goes from village to village. The solar power or the light source in that boat is a solar panel, no hurricane or no kerosene. And boat is fine, good. In the middle, we have a picture here from Casablanca, Morocco, where they're using more public transportation, which is electric, not using cars as much downtown. On the right-hand side is an example of hydroponics. They grow like lettuce, other leafy vegetables inside a room, building, typically abandoned warehouse in the US, no soil, using moisture, fertilizer, and light to grow vegetables inside. If you grow in in the downtown area, in the city, you're not shipping it from a agricultural land to far away place to use it. So what I'm saying here, as an engineers, we should focus on as individuals, what can we do to reduce carbon footprint? Maybe drive less, use more solar, and be familiar with the local agricultural opportunities. I have people who ask me this question, well, I do this in New York, somebody in another country, somewhere else, it doesn't do anything. So what's the point? It's true. If you are consuming less, using more renewable, somebody else elsewhere is using more coal, the sky doesn't know the difference. But my point is, don't ask why they are not doing it. Do your part. Then you have a moral high ground to make it more acceptable down the road. So this is my last slide. With COVID-19, things are getting complex, but the good things also happening, because look at this meeting today, this webinar. If we didn't have COVID, I will go there or this would not happen. Now we found a way to collaborate, cooperate by doing things remotely, which is working quite well, in fact. But for that to happen, I believe IEEE needs to be broader based. And we should be inviting people from academia, industry, government, consultants, so they can all contribute. But for that to be successful, we have to make sure every volunteer feels they are valued, they're wanted, and they have a way to move up the chain to become senior volunteers in IEEE governance. Like you, many of you on this call today are with the Turkey section. So I want to make that open to the younger generation so that they can feel they will be able to contribute. So this is my last slide. Again, as I say, I'm running for president. That's not the point. I'm giving you my email address here. I know there'll be questions today. Maybe you would not have time to answer all of them. If I cannot answer all your questions, please write to me at this address. I'll answer them for you. If you want to find me elsewhere, I can be found in Facebook, LinkedIn, Twitter, and YouTube. And again, my website is here. More information is here about my research and about these lectures I'm giving globally today. So with that, Professor Omer Usta, I'll stop right here and I would stop sharing my screen. Thank you. Shimei, you can take over.
Okay, thank you very much, Prof. Rahman. It was very interesting presentation. But at the end of your presentation, what I am considering, nuclear power will be in a big agenda again, I think, very, very near future, I think so. Okay, thank you very much for the presentation now. And before giving the floor to the Ferit, I would like to remind you, if you like, you can write your question to me. And then by addressing to any one of the speakers or three of them. And at the end of the presentation, when we complete all the presentation, I will direct your questions to the related person or three of them. Now, now we are going to have the second presentation. And the first speaker will be the Ferit, and from the Quanta Technology. And the Ferit, the floor is yours. Okay, you can start your presentation. Thank you very much.
Great, thank you, and good evening all, and thanks for joining today. And it is my honor to talk to you all over this venue regarding the how we can, as engineer, get engaged and do our share of overall reducing the global effect of the industry. As mentioned earlier, I'll be talking about the technology, and I'll be sharing this presentation with my colleague Shadi. We'll focus also on some part of the technology, focusing on reducing the carbon effect of our electric industry. Basically, we will provide you with more of a North American context on what we are typically focusing on when we talk about clean technologies and services associated with reducing the carbon emission in our electric industry, and also helping more globally with all the different industries associated with the electric grid. Professor Rahman actually helped to kind of pave the path to our discussion and more focus on the technologies. As he mentioned, in North America, similar to other parts of the globe, we are primarily focusing on in adding more renewables to the grid, the deployment of the solar, wind, and all other renewable technologies as the primary source of producing electricity has been the major part of the movement. Recently, it's been paired with energy storage systems that I'm going to talk about a little bit more also, primarily to phase out all coal-fired power plants, and in addition also to reduce the peaker power plant, which primarily use gas and diesel. The other movement is around electrification of the industry. And this means not only trying to provide a clean transportation, more for moving toward electric vehicles for both commercial use, fleets, which is actually the dominant part of the transportations and electrifying the transportation areas, and as well as trying to turn a lot of different industrial agricultural processes to use electricity rather than the other polluting source of the energy. And also we are getting involved with what means in general non-wires alternative, which is primarily putting all different solutions together. As we know, typically one area would not work, so we could increase the renewables, but we also need to focus on demand and energy efficiency as the other opportunities, and engaging the entire society in the whole process. Professor Rahman actually a little bit talked about this, that it's not just one, it's the multiple areas that needs to be get engaged, and how the society as a whole can help with this process. So we'll talk about that, what non-wire alternative technologies are and how they help with this achieving a zero carbon grid. And last but not least, we'll talk a little bit about the carbon capture and storage programs, primarily from the perspective that even if we start today, there is already a lot of CO2 emissions in the atmosphere, and we do need other ways of reducing the content, the carbon content, beyond what we can achieve with the other technologies. So one of the methods would be the carbon capture and storage, which is a technology in progress, and we'll talk a little bit about that. But generally where we are coming from, so this is really what happened after 2015 Paris meeting on what globally we can do to reduce the CO2 emission. There is right now more than 200 cities in 11 different states across US, which have established or accepted very aggressive targets to either reach 100% green clean energy content, or become 100% renewable penetration. Basically means all their electricity would come from 100% renewable energy. And this is, as examples, you may have heard about the California case that by 2030, they are targeting at 60%, and by 2045, it's going to be 100% renewable, zero carbon on zero carbon emission targets. And many other states have very similar targets or established the targets. Obviously, what the target helps is that it pushes more the government and different industry sectors to do their own share and think about how they can achieve these type of targets. And it also follows a movement in other places in Europe, countries in Europe that has very similar or close targets of major reductions in greenhouse gas emissions, or achieving energy efficiency and renewable deployment as a dominant part of the energy industry. They are supported by looking at some of the facts that Professor Rahman also talked about it. For instance, in US, in North America, the renewable energy production has been doubled in 10 years. So we're going from 2008 to 2018, you see the doubled, and we have almost every year twice more electric cars on the grid. So this might be seen as a very optimistic approach of trying to reach the 2015 zero emission, but there are movements started, and it supports these these targets, and helps to push both the technology at one end and also the industry to think differently and be able to advance the technology as needed. So that was the optimistic approach. As normally said, the optimistics are the one that get the work done. The pessimistic approach is kind of shown here. Obviously, we are trying to achieve the decarbonization. We're trying to deploy renewable energy, and at the same time advocating for the fact that we need to increase the reliability of the grid and the resiliency toward the different either natural phenomena or any other cyber attack. As mentioned, it's not just one industry. Every single industry has to be get engaged. So by doing more share of the renewable, as you can see, the prediction is that electric power industry is going to actually see a major reduction in carbon dioxide emission. However, there are other industries like commercial, residential, or even transportation, depending on how fast we can deploy the electric vehicles, which see a much lower change in the emission level. So what this pessimistic view actually tells us is that we really have a lot to do, and the focus in terms of the solution is that we need to focus more on the residential commercial approach. Industrial, agricultural focuses a lot on reducing the carbon emission content also. And we can only achieve this if we really have more and more communities like this one on the bottom right corner that entirely fed from solar and energy storage system. And we start seeing all the gas stations have places for charging electric vehicles. Those are some of the major components of achieving the zero emission industry. But on the same time, as mentioned, the carbon capturing programs has to evolve also. This is essential primarily because, as we talked about, there are still industries that we are not targeting, or there is not a simple solutions to reduce the carbon content. Air travel industry is one of them. One of the huge industries contributing to the emission, and there is less methods or mitigation methods available at the moment. Mining and construction industry is one of the other larger contributions, and effective method would be primarily carbon capturing technologies that would help with reducing the carbon content in these industries. However, the fact of the matter is that carbon capturing technologies, although it had a lot of progress, still it's almost cost triple than any type of renewable energy deployment programs. And the total capacity available globally is really just very small at the moment. It's 4% of the just if you look at the emission from the Canada, even though Canada and North America has more than 70% of the deployed carbon capture technologies and plants, but it can only capture about 30 megatons. And compared to what was earlier mentioned about, we are dealing with tetratons of CO2 emission every year. So the capacity is really small. However, it's doing its own share as much as possible. So what my team and other consultants in North America is primarily focusing on is helping our utility industry, or main electric utility customers to determine methods that they can bring in and integrate more distributed energy resources, obviously primarily rooftop or ground-mounted solar PV systems, fuel cell, wind turbine, or even convert many of the power plant to the combined heat and power in form of district heating, add energy storage system, and also utilize electric vehicles in the form of vehicle to the grid. So we can do a share of the energy production in the renewable forms. At the same time, as mentioned, we are focusing on introducing a demand-side management programs or technologies in form of smart thermostat, building load management, heat pumps, and even Internet of Things that help overall manage and reduce the peaks during the time that the system has a high demand. So we would avoid turning on a new power plant at those times. Engaging with the industry to utilize large flexible loads to perform demand response time programs, and at the same time looking into how to improve the design of the residential commercial buildings to become more and more energy efficient on that grounds. But one of the challenges that when we talk about renewable energy programs we face in is that, as you all know, renewable energy is very intermittent. And you may have heard about this issue of the dog curve, which is a major challenge facing the North American utilities. Basically, what it means is that when we start actually approaching a high penetration of renewables, this is as shown in the graph on the top right corner, the PV mostly producing during the daytime, and at the peak it starts reducing the daytime load. So you see this very deep valley of the aggregated loads or the gross load, that once the cloud comes in, or for any reason the PV production drops, then the grid is going to see a very sharp increase in the demand, and that's very challenging for the system operator to ensure that they can match the rising demand due to the fluctuation of the renewable energy, and make sure that the grid is reliable and they can still provide the balance of the generation and the load. As a result of this fluctuation, frequency can suddenly shift, and power quality of the grid is going to get affected. So this would become a major impact. In addition to that, adding more renewables distributed across the system pushes the voltage across the system up, and that's another challenge to how to observe and manage the voltages and ensure that still we can provide a reliable and observable grid for the system. This type of dot curves, as you can see, can be seen now many places across North America. This is in California. This is actually more northeast area of the grid, and that because of the high penetration, we can easily see this type of curve. And the focus is more on load forecasting and generation forecasting technologies that takes into account detailed climate change, so they can provide better day ahead and an hour ahead real-time forecasting of solar and wind system to integrate in these type of 100% renewable system. The other thing that has been becoming more and more focused these days is integrating renewables and pairing them with the energy storage system. Obviously, if we don't have a solution for intermittency of renewables, we get to the point that we have to curtail more renewable energies, which is primarily a waste of effort. So what is solar storage does, which becomes the key components of the new modernized grid, is helping to smooth out the fluctuations and make the renewables much more dispatchable and predictable from the perspective of the grid operation. There are several very large-size solar and energy storage plants being deployed and implemented in North America. This is an example of the plant in Nevada, which is using 180 megawatt of solar, 240 megawatt hour of energy storage to run just a data center for the cloud-based solution providers. One conclusion here is that, or observation, that technology is out there, energy storage, renewable technology is out there. What is really needs to be done is more focus on engineering of the solutions, how we can properly utilize the best chemistry for energy storage, combine it with the best engineering practices in terms of the design and integration, and obviously enablers such as power electronics that would help together to make the application a viable solution. So the technologies are available. However, in many cases, what we see is that applications are not mature enough. And that's really becoming the more focus in North America that my colleague would also talk about it a little bit more. And before just turning the presentation to my colleague, I wanted to also talk about impact of the electrification. It was also mentioned earlier presentation that we're trying to turn everything to the electricity. So, and that's the must, but we need to be aware of the impact of the electric vehicles, especially in the large numbers, on the electric grid, and what would be the peak demand. The forecast, again, as modeled here, shows that in all the different areas of commercial, residential, and industrial, we're going to see a major increase in the peak load. Obviously, it's not across the grid. It's very localized impact on the grid. And we do need to look for the hybrid methods. One method mentioned here for the superchargers, EV superchargers, that really requires a large amount of electric supply, would be to pair them with the battery systems, again, to manage the peak demand. So the key for decarbonization of the electric industry is really also to invest on more robust and hybrid solutions that my colleague would be talking a little bit more about them. Shadi, to you.
Sure. Hi, everyone, and good evening to all of you. It's really interesting opportunity to be here, and hopefully this presentation would be useful to all in terms of understanding how technology can kind of help with reducing the carbon emission and kind of help with the environmental aspects of it. So Fareed talked about the overall technology and the role of technology overall in the power industry today. And I'm going to talk a little bit more about the kind of a hybrid sort of utilization of these technologies, and more specifically on non-wires alternatives. So the term might not be familiar to you all. So just to introduce this term, it's actually kind of, this term is utilized in comparison to what utility is currently doing as their conventional way of addressing the reliability issues and the needs of supplying the customers within their premises. And this non-wires alternative really is referring to utilization of more like greener and clean sustainable technologies as a replacement to, let's say, using wire solution and installing, let's say, another power plant for additional generation, or upgrading the utility infrastructure to make sure that the load is supplied. So obviously there has been this kind of utilization of solar energy, wind energy, and all the renewables energy long ago. And but what is happening right now in this industry and the utilities, especially in North American utilities, is that they are realizing how important it is to have this clean and sustainable range of technology and solutions in their sort of portfolio of solutions, and have them as new services integrated into day-to-day electric utility operations. So utilities are now trying to kind of incorporate these resources, these renewable energy resources, and the kind of clean technology into the planning stage of their, let's say, selecting what solution could be implemented to address the needs of the customers, and also in their operation and maintenance, how the system should be operated and maintained afterwards with the kind of utilization of these resources. So it's kind of a harmonized sort of utility, let's say, effort in terms of having those solutions as part of their portfolio. One of the best, there is actually a wide range of NWA solutions being implemented, from microgrids, battery energy storage solutions, distributed energy resources, demand side management, energy efficiency, and all that. And I'm gonna, through the rest of the slides, I'm gonna talk about some of the examples of these implementation in the North American utilities, and kind of their outcomes, really. So if you go to the next slide, one of the most successful really implementations of NWA solutions, the non-wires alternative solution, is the Brooklyn Queens case. So it's been kind of part of the Con Edison utility in North America. It's actually in New York area, Brooklyn. And they were trying to figure out a solution to a 52 megawatt actually load increase in their system. And their other solution, that the traditional way of doing that for utilities, to install a new power plant, which means that we're adding the generation, we're adding to the carbon emission, and upgrading definitely the power delivery system, so that the generation can be delivered to the customers as well. But instead of that, they actually opened it up to a wide range of different solutions. So because the solution is actually that the NWA solution has to be really competitive and has to be justifiable in comparison with the traditional solution. So if there is a kind of more cost-effective solution, that's where the utility can get the approval from the regulators. So really, some of the key highlights of this very successful program has been that they have used a wide range of different solutions. So from energy efficiency programs and demand response programs on the customer side, to installing renewable energy resources such as solar and storage and microgrids as well. And it's been kind of a fully a competitive solicitation. So whoever can kind of provide a solution at a cheaper price would actually win. So they also suggested some time of use rates and feed-in tariffs that kind of encourages the energy consumers to sort of manage their use of energy, and in order to reduce the sort of the peak demand, and also real-time and peak power pricing as well. So all of these elements together with kind of more engagement from the customer side and encouraging them to, let's say, install the behind the meter energy resources such as local rooftop PV solar systems or other generation, and also utilize the smart thermostat or other kind of other technologies to reduce their demand and manage their demand. The combination of all of that makes the Brooklyn Queens case a very successful NWA implementation, where the utility was able to justify really the use of more cleaner and more sustainable solution instead of the conventional power plant installation. Going to the next slide, another kind of case study that has been a very successful, and it's a very high profile project in North America, is the Nantucket Island energy storage system. So Nantucket Island is one of the islands and located in near to Massachusetts area, and it's definitely an island which is kind of supplied by 2 submarine cables and also some on-site diesel generators. And as you might know, the diesel generator is one of the kind of dominantly used generation sources for islands. Which is kind of a very polluted sort of generation as well, and the preference is now to kind of reduce as much as possible. So in order to really address the issue of the reliability issue of feeding the island customers while there is a loss of one of the cables that are kind of supplying the island, and also sort of based on the increase in the demand of the island during the vacation time, during summertime, because this is a vacation destination, they started to install this 6 megawatt, 48 megawatt hour battery energy storage system connected to their sub-transmission system. And using this energy storage system solution not only helped them to kind of displace the utilization of the diesel generators for supply of the island, but also it helped a lot with being able to also add more PV solar generation, more clean generation on the island, because the battery can kind of capture the energy from the PV and release it whenever needed. So that was another benefit of having this solution completed. And also another important thing was that because the battery was capable of also reactive support in the system and voltage control, it also helped the system, the overall system, for energy saving and kind of loss reduction in the island. The technology was really implemented, and it was a key aspect. But I think one of the highlights of this project and what makes it a successful implementation was that there was an extensive level of studies to design and engineer a solution for this specific purpose, so that we can gain all the benefits from the technology. And just to kind of maybe highlight the role of an engineer in terms of design, engineering, and testing the solution, it's very important that all of that be in place so that the solution works as it's supposed to, and kind of do whatever it's supposed to provide to the system. So I think the next slide, maybe this is another kind of example of a community energy system. It's Bronzeville Microgrid. Bronzeville Microgrid is one of, again, another high-profile examples of microgrids, which is kind of installed in downtown Chicago to supply a community of different critical infrastructure and residential and sort of commercial customers as well. It's been strategically co-located in the vicinity of the a campus microgrid, Illinois University IIT campus microgrid. And really the importance of the microgrid technology here is to make sure that all the different resources, let's say if you're putting PV, battery and all that, all these resources can be aggregated and used to efficiently to balance out the energy demand and the energy production of the system, the local sort of energy production, the system. So for instance, the picture on the right, bottom right, is actually the 17 buildings that are currently part of this microgrid. And they have all rooftop PV systems as part of the microgrid. So as Farid mentioned, the intermittency nature of the renewable generation makes it difficult to have it captured at the time of the need. So like aggregating that kind of helps to balance out the generation and also utilize it, capture it using energy storage, storage system also in the mix of the microgrid generation to make sure that we capture it whenever it's not needed and then release it whenever there is a need. And also that's the same kind of story with the sort of two microgrids in the neighboring of each other. When the IIT microgrid has more generation and the Comet, the Bronzeville microgrid, has more demand, so utilizing and coordinating these two together can help us sort of balancing out the energy needs. And that is done through the kind of coordinated control utilizing the microgrid controller and the technology here. So if we go to the next slide, really one of the promises of the technology for modernized grid is having a smarter, more efficient grid, and where we can collect information from the system and utilize it, first of all, for monitoring purposes to know what's going on in the system, and also to be able to control the resources more efficiently and in a coordinated fashion. So DERMS is actually distributed energy resource management system, is one of the platforms that is dedicated to manage the distributed energy resources and that are kind of penetrating into the grid more and more, and to be able to kind of aggregate them together and make sure that we can optimize the resources and control them so that we can get the most out of the resources that we have. And it's kind of DERMS is a more business centric, so it kind of is an enabler for all the different resources, like behind the meter resources also as well, for the customers to be able to participate into the electric market as well. So that's one of the use cases. But more importantly, kind of being able to coordinate all the different resources and make sure that you utilize them at certain times of the day, makes it easier for us to kind of manage the production in the system and increase the room for adding more and more renewable energy generation into the system by kind of balancing out for the intermittency nature of the system, these kind of resources as well. So the next slide, I think that's going to be the last slide. It's kind of this slide is for mainly emphasizing on how important, like we talked about all these use cases and how all of the applications help us getting into the state where there is less and less of carbon emission from the power plants that we talked about. But really the technology is the heart of the changes that it's happening in the electric industry. Without that, this cannot really happen. And smart inverters are the power electronic based devices that kind of comes between these renewable resources and the distribution grid, and enable us for having like extensive monitoring, data analytics, communication, and controls. And I think really the point is that as engineering consultants in the area of renewable energy, we should be all trying to understand the technology better and making sure that it's implemented properly to bring us closer to the target of utilizing clean energy resources as efficient as we can in the system. So with that, I would like to hand it over to Farid for the conclusion slide, and we'll be happy to answer any questions afterwards.
Thank you. So just to manage the time and I guess patience of everyone that's been listening today, we wanted to close with this main comment that as we talked today, electricity is really the key for achieving a carbon-free energy future. And what we see in that that global effort is first of all, modernizing a grid is it's a main part, ensuring that we have a resilient and reliable grid, and we can provide a platform for more innovations and optimization of the way that we utilize technologies through the modernized electric grid is going to be the focus, and lots of investment is also going toward that aspects. But more highlighting the fact that societies like IEEE and what we are all here today is really geared toward providing the venue for technology advancement that is needed, educating our workforce, develop standards, and also provide a method of sharing the global best practices similar to the one that we talked today. So all throughout the globe, we can benefit from what everyone is doing and how they're trying to achieve the goals and target, very aggressive goals and targets set for these purposes. And hopefully we can all go back to the future and enjoy a much more clean and sustainable environment. So I'm gonna basically end it up here with the quote that says that basically we need to all do it together, and the focus is to win it together, not everyone or individuals. Thank you again for this opportunity and the time tonight, and we'll be happy to discuss any questions or hear comments or your view. Thanks.
Right. Farid and Shadi, thank you very much for your interesting presentation. So now the time is question and answer time. So I've got a few questions, and then the first question I think comes from Berk Buzcu. What are you saying about it? World is moving away from coal, and that's great in terms of global warming, but hydro solar panels are said to be affect local fun, i.e. solar panels farms are increasing the temperatures in the area they are placed in, therefore altering the local environment. Could this be a problem in the future once the solar panel farms are increased a lot of in number? So following similar pattern to global warming, solving a crisis but creating another crisis. So that question, I think, goes on Professor Saifur Rahman. So
I'm not sure I understood the question fully. My point is, yes, we'll have more solar panels. You saw in Shadi's and Farid's slide, Chicago, Bronzeville. I work with Bronzeville quite a bit. All the roofs are taken. Case of the in Queens case, roofs are all taken. So we will run out of space in cities pretty soon. We want to put solar. It cannot possible, not possible. So the solution is what we call a global energy transfer for two reasons. One is Saudi Arabia has a lot of land, not many people. But the question then is, how do you bring the Saudi solar power to New York? That's the question. So you build a lot of high voltage transmission lines, all of that. So my point in short, yes, you're right. We cannot cover up all the roofs of this country in the US, not enough roof left to do solar, not possible. But we have to also use renewable to clean the atmosphere from CO2. So only solution is put this solar where the land is in the US, Texas, Arizona, New Mexico, Southern California, then the upper Midwest, North Dakota, South Dakota, a lot of space. So the answer is the following. Build a very strong transmission grid, number one, and put solar where the sun and wind, also the wind is, and bring power to the local area. One final example, in Virginia, offshore wind, 3,000 megawatts. Each 6 megawatt plant, and they will have 500 of them. We in Virginia cannot use that much power, we don't need it. We'll push that power through undersea cable to New York City and Boston areas. That's an example of how the remote area sources can be brought to your neighborhood. So I'll stop here, Professor Costa.
So thank you. But the question is, he's saying that, yes, we are installing the panel, okay? We are installing the panel. So that is good. He is saying that is very good. But that solar panel also increase the degrees and increase the temperature of the environment, he says. Is that correct?
Yes and no. Yes, you're right, because the ambient temperature is about 10 degrees cooler than this solar panel temperature. That's true. I'm in my lab, I see that. Ambient about 85 degrees Fahrenheit, solar 95 degrees Fahrenheit, the back of the panel. That's true. So that is releasing heat. That's true. But that is very quickly moved away by wind blowing under the panel. So my building is no more hotter than it used to be. My one building, I measured that for that reason. So it is
no environmental solution, but that's a good thing, no environmental solution. Right. Sorry about environmental problem.
Correct.
Okay, pollution. Now the second question, I think, coming from, let me check it, from our president, Professor Dr. Fadik Urda. He says, the question to Professor Dr. Saifur Rahman. He said EVs energized by coal do not reduce carbon footprint. Are EVs more energy efficient?
That is true. That is true. What I'm saying, yes, you're better off using electricity in a car, regardless of the source of the electricity, coal is okay, compared to gasoline-based power. So if you drive 100 kilometers, example, using a gasoline car, you produce some global warming gas. You drive the same 100 kilometer of that another car using electricity made from coal, you'll produce less global warming gas for sure, overall. True. But the point is, if you could run that 100 kilometer car using electricity from wind power, you'll produce much, much less CO2. That's what I'm talking about.
So that as long as the electricity coming from the renewable power generation, yes, his car, that's good. But if the electricity coming from the coal power plant, that is completely different. For the electricity cut, I am talking about EVs.
Right.
So then, by the way, Ferit and Shadi, would you like to make any comment on one of these questions?
Well, I can just maybe quickly talk about the the first one was mentioned, the first question. I believe they were discussing the issue with the recycling at the end of the life of the panels, in addition to potential, perhaps the warming effect of the environment. So that's definitely that's part of the technology design and the whole life cycle process of the being a sustainable solution. So it is not just to focus on solving a problem now and perhaps postpone the problems to the future or create a few problems for the future. So when we're looking at a sustainable approach, we are looking at the entire life cycle of the technology. So there are recycling methods for PV panels, and same way that at the same time that we are developing energy storage systems and cells and using it for the grid, we are looking at energy storage for electric vehicles. At the same time, we are looking at the second-hand battery systems too, and how to utilize the second-hand batteries for different applications to manage the whole life cycle. So yes, it is a challenge. It's a challenge of making sure that it's a sustainable solution, and we are not just simply turning the focus from one problem and creating another problem. But that's basically what we do as engineers, trying to address the issues and ensure that it's a clean and sustainable solution.
Right. So I got the next question will be from me. Okay. So if Professor Rahman, when you read the report about the International Energy Agency's report, the latest report, what is saying about it? It says the use of I'll tell you, use of renewable energy is something around 26% in power generation. It's quite well and increase as well. It says use of the renewable energy in heating and cooling is something around 10%. And then lastly, 3% in the transportation. Yeah, it's, so my question is, you see, so what we are doing, we are trying to moving from the present situation to the smart grid, okay, smart grid. So in the smart grid, what we are planning to use the more green energy, okay. So but in order to increase the use the green energy in any sector, okay, industry or transportation or heating or something like that, two things are very important. Number one is the related technology. You need that technology, yes. The second one is the investment, okay. So what is the situation when you consider the transportation? Why it's very low, it is 3% only. Use the renewable energy in the transportation. Is it,
Well,
is the investment, the reason is the investment or the technology, available technology?
If you want to use more renewable in the transport sector, you can put solar panel on a bus rooftop. We have done that, it works. But more practically, to use more renewable in the transportation sector, you have to drive the transport car, truck using electric vehicle, and then make the electricity from renewable. That would be a solution. Now it's happening already. Like Norway has said, starting 2025, they allow electric car to be sold in the country, only electric, 25. You can sell gasoline cars in Norway as a country. So these are government decisions. Somebody might say, well, it costs more to have an electric vehicle than a normal gasoline vehicle. It's true today. But as the battery technology is improving, that difference will go away in 5 years. That's my prediction. Today, Electric car, battery costs 30% of the whole car cost, 30% is battery only, forget everything else. That is coming down significantly. So then the differential in price between electric and gasoline would be close. Then you have no issue of investing. You can buy either that car, electric car or gasoline car. Then the question is range. If you drive 500 kilometers for some reason, you have to charge your battery on the way somewhere. That's not very comfortable. So as the range grows of the battery price comes down, issue of investment will be neutral. Then that's not a problem. Now talk about in the power sector, it's true. Today, it costs about 3 times as much initial cost to make a nuclear power plant compared to a solar power plant, 3 times nuclear cost. Nuclear is no cloud issue, of course. Solar is cloud issue. When you put battery and long distance connectivity, then intermittency issue goes away.
Right. So the next question will be to again, Prof. Rahman. It's coming from the Bülent Bilir, okay, from Bülent Bilir. What he's saying about, what do you think about the solution for environmental issues if we need energy, in particular electrical energy? I am doubtful that renewable energy is not 100% environmentally friendly. Yeah, it's nearly the other question. It's the same, the other question. It says, yes, it's friendly, but it's not 100% environmental friendly.
That is true. I did not show the slide today. I showed the same slide on the other locations. Hydropower is not very clean. Not very clean. Even though no CO2, it makes a lot of methane. Why? When you build a dam and flood the land behind the dam, the land had trees, vegetation, normally. All that is underwater now. Over time, that rots. As it rots, it makes methane. Methane is 18 times more complex than CO2, number one. Number two, as the elevation of water changes from rainy season to dry season, you submerge more vegetation. So hydro is not clean, you're right, but cleaner than coal, that's my point. And other people ask me this question, fine, wind power, solar power, but it takes energy to build the solar panel. It takes energy to build the wind turbine blades. Where's the energy coming from? Coal. So you have used coal, CO2 to make the wind project.
Yes.
We have studies who show for solar, I know, it takes about 3 years to pay back all the CO2 it was produced in manufacturing the solar panel and the glass and everything else. So in the long run, it's okay, but short run, you're right. It is not clean all the way, true.
So before coming to nuclear power, that one question is coming from, I will tell you, and coming from, yes, Ömer Melih Gül to Miss Shadi, okay. What it says, Ömer, about it says, and load forecasting, which has been studied for a long time in academia, and I consider this way as well. What is your practical solution for load forecasting, neural network-based load forecasting, machine learning-based, using regressing lines? So that is, I like this question because it has been that the people has been, working on the load forecasting loads for several years, okay, maybe several decades, but the result, and I don't know, result of these, we don't have, I consider, we don't have a clear answer, okay, from these studies, like the frequency measurement, okay. So when I was in the UK, people working on the power system frequency measurement, several projects in the United States, in the United Kingdom, okay, and where say several projects have supported from government and the other for frequency measurement. But at the end of the result, I mean at the end of the research project, they have got the same result. So if this measure the power system frequency very fast, it's not trustable. And if it's not reliable, if you measure it, if you want to measure it in a reliable range, it takes so long time, especially under the power system condition, okay, faulted condition. Now, I consider nearly the same than the load forecasting. We need it 100%. I believe that for economic reason, but that the result nearly the same to me. Okay, every research project result coming from different results project exactly the same for me. I don't know, maybe. So the question is going through the Miss Shade, okay, from Omar. Another, we do have two Omars. Okay. I think we do have a...
Shadi, do you want to take that question, or you want me
Sure,
to?
I can start and Farida can complement.
If
Very
you like,
interesting
Shadi,
question,
I
by
will
the way.
read it again to you, okay?
Yeah. No, I actually can see the question. So
Yes.
yeah, so they're asking about load forecasting, which has been studied for a long time in academia, and what is the practical solution for load forecasting, neural network-based, machine learning-based solution using regression lines, I would believe they meant. So I think like I would just make maybe a more general comment, and that's we talked a little bit about the data analytics and how the role of kind of processing the data, because we're right now we're kind of moving towards a smarter grid. We're collecting data from all different meters, and then we have these smart meters all over the place. Like we have a lot of like measurement devices that we're collecting information from, and so kind of dealing with this data and sort of data analytics for different purposes is kind of becoming a very trending topics in the industry. In fact, and kind of AI is one of the also kind of the methods that being implemented. And interestingly enough, one of the projects that we talked about, actually, they are doing load forecasting, AI-based load forecasting for the National Grid project that I was talking about. So they basically kind of forecast what is the load based on the kind of training their algorithm based on the historical data. They forecast the load, and based on that, they dispatch the battery energy storage system. So they would tell that how much the battery needs to be producing in terms of the active power output based on the load forecasting. And I think that's also one of the very key elements of the DERMS platform that we're discussing. So especially that is important when we're talking about market participation. So sort of being able to forecast the load utilizing different methodologies, which AI is one of the kind of the hottest topic right now, is also part of the DERMS platform, being able to understand what is the load in the system, so that you can kind of provide your generation, coordinate the generation accordingly as part of the control of the resources as well. So if the question is that are we kind of having applications currently in the industry, I should definitely say yes. But kind of more specifics of that, I would probably maybe leave it to you, Farid, to comment more on that. But that is generally the applications are growing in the industry as well.
Right. So I'll address the second part. So yes, load forecasting, similar to any other technology, can have error, and I mean there is no let's say perfect method of forecasting load. It's actually less accurate to forecast solar, and I mean many climate level and events can actually change the solar, wind forecast, generation forecast. But overall, the way that industry approaching it is not just to take the load forecast and then set everything according to the given number. It's a very closed loop, real-time forecasting. So we'll do a day-ahead forecast, and then that gives us the baseline for optimizing and setting the targets for every hour for the next 24 hours, but we continue the load forecast through the hour and through the hour ahead and 10 minutes ahead, and that would basically corrects the error. And as we go ahead, we have the hybrid approach of utilizing more controls and also having the reserve capacity available through solar storage that can manage the differences between forecast and the real demand or real production. So, the forecasting is needed, but it's not the final solution or final answer. We have to look at it from the perspective of a digital grid and the fact that everything is in the closed loop and a hybrid of various methods to achieve the final objective.
Okay, thank you very much, Ferit. So we do have a second question from Professor Urda, okay, Fatih Urda, President of IEEE Turkey section. What he's saying about, he says, if export is only 3% of carbon dioxide, CO2, why are people make a big deal about it? To the Seyfur Rahman question.
Ömer Hocam, transport.
I understand.
Transport.
Transport. Yeah, if transport is 3%, yes, it was coming from the International Energy Agency. Yeah, transport is 3%. And it's, well, but I don't know really, but my saying is, my explanation was the use of renewable energy in transportation is only 3%. Is that related with your question? Okay.
So I understood it as, Ömer Hocam, I understood it as the contribution of transportation in carbon emissions is 3%.
No, that's not correct. The International Energy Agency report says use of renewable energy in generation of electricity is about 26%, 10% heating and cooling. I mean, use of renewable energy in transportation is about 3%. Okay, so that is this means that is very low. How we are going to increase it? Something like that, not related.
Okay, then please ignore my question.
Okay, thank you. So we do have one more question to Professor Rahman, coming from Sergen Selki. It's something says, what do you think about the children in power? Yes, women in power, now children in power. But he says, do you think that environmental and energy problems of the future can be solved at a young age now? I mean, about what will be the contribution of the younger generation to the solution of the power system? I mean, the energy solution in developing energy.
That's a very, very good point. Very good point. Children are more idealistic and they are not biased and then worried about their own pocketbook. So the grown up pocketbook, if I turn off a coal plant, I'm losing some jobs. I don't turn it off because a job will be lost. Children are idealistic. And then if I educate my grandkids about solar energy, they can go to home and tell their father and mother, you should do this. So in the US, we have done that. We have put in elementary schools 6, 7, 8-year-old kids classes, talk about energy efficiency, talk about solar energy, talk about how you can make your room cleaner CO2-wise by using solar energy. So they go home and tell their parents to do this. So we'd have a children in power group, bring them to our general meeting and give them some more education. That's a good idea. But we have to, maybe Shimai can address, she's a women in power person. Maybe we can make children in power group. Thank you, good idea.
But at the end, he says, rather than children, young age people, he says,
right,
younger generation.
Teenagers.
So these were our question, but the final question is, as I said just after your presentation, And when you make a prediction, okay, prediction about the future of the power generation, yes, well, the renewable energy and nuclear power plant, okay, and nuclear power is, you know, appearing, okay, as far as I understand. What do you say about it? What do you say about the future of the nuclear power plant, power generation? If you can hear me.
I can hear you. Yes, I can. So can you hear me?
Yes, I can hear you.
Okay. So nuclear power plant is risky for two reasons. One is money, other is nuclear fuel. The fuel is not available in open market. You have to contract with the supplier. Globally, there are 6 or 7 countries can supply nuclear fuel. That is why China is not going nuclear. It's only 4%, 10 years from now. They don't have uranium stockpile. They don't want to be dependent on Australia or other countries to give them fuel. So they are staying away from it. You saw the slide that Farid and Shadi showed. Nuclear contribution going flat, not growing globally because of the money issue and the fuel supply issue.
I think we lost the connection.
Can you hear me now?
I can hear you. Okay, that's
Okay.
clear. Right.
So nuclear is going to be controversial because of investment issues, 3 issues: investment, number 2, security, nuclear accident, and 3, fuel issue. The whole idea with some countries want to build nuclear plant and they want to do fuel processing. Whole thing about Iran and US problem, same issue, the fuel issue. So this is going to be a problem forever. That is why nobody is, look at Europe, they build not except France, nobody building nuclear. Finland is building one with France's support last 15 years, still under construction, 15 years. America in the last 30 years, only 2 nuclear plants, just two. And you go to China, very few. Turkey, maybe starting, I don't know. Egypt talking about it. Middle East, nothing except UAE. So nuclear is, on paper, looks good. In practice, a lot of issues.
So we do have only one option, renewable energy. Is that correct?
And natural gas in the meantime.
Natural gas. Yes.
In the meantime, right.
So, well, so these were our questions. Okay, we don't have any more questions.
I have one last question.
Yes, please. Go ahead.
Has anybody quantified the reduction in carbon emissions during the COVID times?
During what times?
COVID,
During
Corona times.
Oh, of course.
pandemic
Yes.
times. I mean, during the pandemic times.
Yes. What happened, you'll see 2019 and 2020 data, maybe 2020 data much better. Because we are not going to office, not burning petroleum in my car, number 1. We're not working in the office. My office is not running air conditioning as much as they used to. And we're not going to shopping. The shopping center is not running very much. So for these reasons, transportation, power generation, and industrial production have come down. And if you look at the data for 2020, CO2 emission will be 20-30% less than 2019 data.
20% less?
Than 2019 data, yes. That's my guess. 2020 is not over yet. We still have 4 months left.
Right, but we can compare on a month-to-month basis, right?
Yeah.
Right?
20% right now, you're right. Right now. Will be even more by the end of the year.
I consider it's related with the decrease in the use of energy.
Right, right.
Okay, any more question? I think we don't have any more question. And I would like to ask the speakers, do you have any final comments about your presentation or anything to us?
Well, first of all, I would congratulate you starting with Shimai. We talked with her long time back when at 10 o'clock Istanbul time, the idea came up. I talked to Professor Omer Usta many times for other things like the TND conference. And we talked to Fatih on email. So I'm very happy that you have a very strong, dedicated group of engineers, IEEE members, who are able to come to work very quickly. Idea comes to somebody's head, you come together and make it happen. So I am very happy that I have been able to come before you and share with you my thoughts. And I would hope we can continue doing this for the next multiple years going forward. Thank you very much. I hope I can come to Istanbul sometime soon, maybe next year, and do a meeting with you face to face.
So I was planning, we were planning actually a meeting. You are planning host you here in Turkey in this month, okay? And then for a meeting, okay, something like that. But now we are doing it on computer. That's good. So Ferit and Shadi, thanks for your presentation. Okay, it was a good presentation, nice presentation. Have you got any final comments? Okay, do you have anything to say us?
Just saying thank you to you and also all IEEE members in Turkey. This is a very late night time actually in Turkey, and we really appreciate that everyone has stayed with us until this time and participated. Hope we can continue more discussions, sharing our experience and as we discuss best practices through IEEE or any other venues in the future. Thanks for you also for organizing this, and thanks to Dr. Rahman for nominating us for this effort. And everyone stay safe and conscious. Thank you.
Okay.
I would like to also thank you, all of you, for organizing this interesting event. I hope the participants could gain a little bit more on the perspective of technology and its role in this kind of the whole equation. And also thank you to Dr. Rahman as well for presenting that. It was an interesting discussion overall. And hopefully we can have future discussions as well.
Thank you very much. By the way, Professor Rahman, Aydin Çetin right now is in a holiday, but he is with us, okay? So if you like, and I say thank you to Aydin and to all the audience as well, okay? So before giving the microphone to our president, Fatih Uğurda, I would like us, the Tuncer Baykas and the Shimai, do they have any comment, any final comment about tonight, okay, about the presentation or anything to say?
Well, I would like to thank everyone, and also I would like to announce that we are going to put this webinar in our YouTube one more time. So soon actually you can find it, and then maybe the audience would like to share with their colleagues and students as well. Thank you again.
Okay, Shimai?
Thank you so much for everyone being here, and we're really honored to have our speakers today, and thank you so much for your time and connecting with Turkey section members and our guests all around the world. So because I'm seeing also some faces from the other sections in IEEE, and thank you for being here and for your support and sharing your knowledge with us. Actually, after handing over the floor to our chair. I would like to also ask, if possible, to just turn on your cameras and have a screenshot from the session as a memory. Fatih Hocam, before you or after you?
Before me.
Okay, all right, sure.
You have the final
Let's spend the last few minutes with our cameras on.
Awesome. Thank you so much. And then we'll have our final remarks from our chair. And we appreciate for everyone. Of course, for the camera, there's no pressure. If you want to be in the picture, that will have several pictures. Just the memory from the session, because you were with us entire time, and we appreciate also for your time. Okay, so just like to wait one more second, couple of more seconds, just to make sure if everybody's fine. I think we are good. So again, as I said again, no pressure to turn on your camera. If you want to be in the picture, you're welcome. So okay, great. So we are actually pretty crowded, which is awesome. And then I'll take a couple of screenshots. That's why I'll ask you to wait a couple of seconds. So I'm going for the first one. And second one, I'll take 4. Okay. One lost. The third one. And the final one. Thank you so much for your patience. And I would like to give floor to our chair.
Thank you, Simay. First of all, I would like to thank our speakers, starting with Professor Rahman. Thank you so much for being here, for sharing your thoughts with us. The same goes to Farid and Shadi. We really appreciate their discussion, their answers and everything. And last but not least, I thank all of our audience, all of our members in IEEE Turkey section, and we'll continue to organize webinars on relevant topics like today's. And before I close this meeting, I would like to introduce our public relations coordinator, Bülent Hocam, can you wave? And I would like to introduce him to Professor Rahman for a second time.
Yes.
Thank you so much. And again, actually, this is the last but not least part. Thank you, Simay, for organizing it. Thank you, Ömer Hocam, for organizing it. Thank you, Tuncer Hocam, for contributing to it. So, Simay, you want to close the meeting?
Sure. Thank
you,
you
the host.
Sure. So this actually we're wrapping up.
Okay, Ömer Hocam wants to say something, I guess.
No. I will say women in power again.
Women in power, yeah.
Yes, Simay will do it.
Right. She has all the buttons.
Yes.
Whistles and bells. Okay.
Yes. Yes.
Okay.
Thank you so much.
Bye.
This is the end of the session. Thank you, everyone. We're closing up, and see you next time.
Thank
Bye.
you. Bye-bye. Bye-bye.
Okay. Thank you. Bye-bye.
Good night. Good night.
Good night.
Good night. İyi tatiller Aydın Bey.
İyi tatiller hocam. Teşekkür ederim organizasyon için, toplantı için. Gayet güzel oldu. Gayet keyifliydi.
Teşekkür
Görüşmek
ederiz.
üzere hocam. İyi akşamlar.
Görüşmek üzere.